So we'll start our section, that is prologue. Just a minute. Yeah. We'll start our section, that is prologue. Prologue, that is abbreviation for programming in logic, and it is considered to be a 5th generation programming language, wherein the focus is on solving problems using constraints given to the program rather than using an algorithm written by a programmer. Most of the constraint based and logic programming languages and some declarative languages are considered to be 5th generation languages. Basically here the focus is on eliminating the need for human programmer, automatically deriving algorithm given a problem represented as a set of constraints. Let us go further. While 4th generation programming languages are designed to build specific programs, 5th generation languages are designed to make the computer solve a given problem without the programmer. No need to have programmer, automatically deriving an algorithm for a problem represented as a set of constraints. These languages are mainly used in artificial intelligence research. Prolog is mainly used in artificial intelligence research, along with another logic programming language which is very popular, that is Lisp. These languages are not commercially used, so you will not find them in commercial applications. But for AI research, they are highly used. They are extensively used. Examples of other 5th generation programming languages are OPS5 and Mercury. Now, actual work on this 5th generation programming language, it was started by Japan. And in mid 80s and 90s, Japan put much fund into their 5th generation computer system project. And their idea was to design a massive computer network of machines using these tools. But then still this is under research, and the limitation with these languages, the 5th generation languages, became more clear when there was need to build larger programs. It turns out that given a set of constraints, defining a particular problem, deriving an efficient algorithm to solve it itself is a very complex task. Thus, the crucial step of automated generation of the algorithm that cannot be automatized and still requires the insight of a human programmer. State of the art, we are unable to remove human programmer. Still, human intervention is required. However, some good work has been done and is going on. Another example of 5th generation programming language, that is a functional programming language named Haskell. It's a very old language, and it is based on what is called lambda expression. You must be aware that in Java 8, the main addition part, that is lambda expression. Haskell has been using lambda expression years back. So that is another example of 5th generation programming language. Lisp actually is not considered to be a 5th generation programming language, though Prolog is said to be built on Lisp. Lisp itself is considered to be a 4th generation programming language. And compared to Prolog, Lisp is considered to be a lower level language, that is more closer to machine compared to Prolog. These are two important logic programming languages. These are famous logic programming languages, Prolog and Lisp. Let us go to the next page. And before we look into the syntax part, of Prolog, let us look into the fundamentals that is behind that. So let us introduce ourselves to logic, and we start with the basic logic, that is laws of traditional logic. Let me see if I can properly upload that. Going to the next page. Yeah. We'll discuss the traditional logic, then the propositional logic, and subsequently predicate logic. Prolog is based on what is called Horn clause, We'll formally see the definition of on clause after that, and then we'll move to the syntax of Prolog language. Traditional logic, our conventional logic, still it is a logic, and here are well-known laws. Identity, name is identity. Law is a very simple law. A thing always equals itself. Next is the contradiction law. Name is contradiction, and we know A is a proposition. A is not both A and not A. A is not both A and not A. And we know the meaning. No statement is both true as well as false. Next is a little interesting law. Law of excluded middle. As the name indicate, it is excluding middle, no middle values. A is not A, that is the law. And the well-known meaning is every statement is either true or false. Only binary values, 1, 0. Every statement is either true or false, 1 or 0. That is excluded middle. There is no middle values. But then there is a well-known logical system which does not obey the law of excluded middle. A well-known logical system not obeying the law of excluded middle. If anyone can answer this, the name of the logical system which does not obey the law of excluded middle. Please do not look into the Google. No, here we are not testing your knowledge. Unless said otherwise, please do not look into Google. That is not our purpose. Here we are not testing. Any idea if anyone knows? Any logical system which does not obey the law of excluded middle and is a very popular logical system? The name of the logical system, let me give that. It is fuzzy logic. Fuzzy logic does not obey the law of excluded middle, which means it has middle values as well. It's not only 1 or 0. It's not binary values. It is, in fact, a fuzzy proposition is in the range 0 and 1, both inclusive. A fuzzy proposition can take any number, any value in the range 0 and 1, both inclusive. This is actually fuzzy system. Fuzzy logical system is part of your syllabus, and in other section that will be covered in detail. Only this was the introduction. Any idea how many values could be there for a fuzzy proposition, given that it is in the range 0 and 1? Any idea? Range of a fuzzy proposition. How many such values could be there? Yeah, rightly said. Fine, both of you have rightly said. Hetul, Rushi, rightly said. It is infinite. Fuzzy range, fuzzy propositions range, because it is any value between 0 and 1, it has to be infinite. Infinite number of real numbers are there in the range 0 and 1. The numbers are infinite. Range is 0 and 1, both of them inclusive. You'll be studying that in the other portion in detail. This is just the introduction about fuzzy logic. Next, we move to the propositional logic. Let me slowly scroll that. Yeah. Already you studied this in discrete maths, also in TOEFL subject, theory of automata formal language. This you studied. We quickly go into that. A proposition is a statement. A proposition is a statement, and the rules of deductive inference for proposition have been listed below. Here letters P and Q represent any proposition, and here are the rules. First one, if P implies Q, I have not totally shown that to you. The first rule I am discussing, if P implies Q and P is true, then Q is also true. Very simple rule. P implies Q means if P, then Q. And it is given that P. If P, then Q, it is known that it is P. P is true. Obviously, we can conclude that Q is true. For example, if it is raining, there won't be any picnic. Given that it is raining, we can conclude that, we can declare that there is no picnic. So if P, then Q, given P, infer or conclude Q. It is known that proposition Q is true. That is the name which is given to modus ponens. The name of the rule that is modus ponens. Now there's a complementary rule to modus ponens called modus tollens. I'm not going to write that. Antecedent, same antecedent and consequence. Consider P implies Q. If P then Q, that P part is called antecedent. That is antecedent of a rule, the precondition. Then Q, that Q part is the conclusion. So here, if P implies Q and P, so antecedent here, it is P implies Q, even P implies Q. Now in the second part, given P implies Q and it is known that Q is false, can we conclude anything? Rule number 2 I am discussing. Modus ponens already discussed. A similar rule to that, it is if P implies Q and instead of P being true, now what we claim, what is given to us, Q is false. Can we conclude anything? If anyone can answer that. Given P implies Q, yeah, answer is P is false. Rightly said. I mean, we can definitely say P is false. We can definitely say P is false, and the justification is simple. I'll scroll back. Yeah. If P implies Q and Q is false, suppose let us assume that P were true. Suppose assume that P were true. So if P were true, then because it is P, if P then Q, because it is P implies Q, because it is if P then Q, it means Q would have been true. But then it is known that Q is false, which means P cannot be true. Had P been true, Q would have been true, because it is if P then Q. But given that Q is false, P has to be false. And that name of rule, that is the rule what is called modus tollens, that is complement to modus ponens. This is modus tollens. Definitely we can conclude that P is false. This is not inconclusive. Conclusion is there and it is P is false. Modus tollens rule. Similarly, we move to the next rules. Given P and Q, both of them not true. P and Q are both of them not true, and P is true. And because both of them are not true, only option that is left is Q is false, and that is exclusive OR. Q is excluded from being true, that is exclusive OR. P and Q, both of them are not true, and P is true. Only option for Q is being false, that is exclusive OR. And similarly, if either P or Q is true, either of P or Q is true, and P is not true, only left option that leaves for Q, it is to be being true, and it is included to be true. Therefore, it is actually also called inclusive OR. Once again, either P or Q is true and P is not true. So only proposition that remains Q that has to be true, that is Q, and that is inclusive OR. Moving further, now our types of statement. These are very simple things, but as a part of inclusion, for the total inclusion, we are discussing that. Propositional logic, it recognizes 4 possible statement forms that express relationship among 2 classes, the subject class and the predicate class. S is the subject class and P is the predicate class. And here are all those S and P are there. 2 propositions are there. S is the subject class, P is the predicate class, and we look into the various combinations of S and P. True, false, true, true, false, true, false, false. Those are 4 classes, 4 combinations. And among these 4 combinations, for these 4 classes, we have given the examples. We can give any example. In fact, infinite number of examples are possible. All S is P. Class is all S is P. You can take any example such as all Americans are car drivers. No S is P. No Indian is two-headed. Some S is P. Some Americans are taxi drivers. Some S is not P. Some taxi drivers are not aggressive. In fact, this prologue language, it was invented by Cloxin and Melish, and because they are from other countries, US. Therefore, these examples, some of these examples have been taken by the person who has invented prologue. So it is in the context of these are his examples in the context of prologue language, the person who has developed the language. Fine. So this is about the subject class and the predicate class. which are being recognized by propositional logic. And next we look into the inference, deduction, which is finding out new knowledge from existing knowledge in propositional logic, called inference or deduction. And let me scroll. Yeah, look at this example. Look at these statements. All Americans are car drivers. And the next statement, all Californians are Americans. I have made a little mistake. This taxi driver, it is there in the image, so I'm not able to remove that now. All Californians are Americans. The given statements are all Americans are car drivers, all Californians are Americans. We can deduct or infer that all Californians are car drivers. You can, this is our deduction or inference, which means finding out new knowledge from the existing one. That is called inference. The process of doing this is called inference or deduction. You can relate this as a mathematical property, say transitivity. All Californians are taxi drivers. All Californians are Americans. Sorry, taxi drivers is not there. All Californians are Americans. All Americans are car drivers. Therefore, all Californians are car drivers. A to B, B to C, conclusion A to C. So this is using, here we are using the transitivity mathematical property to infer that all Californians are car drivers. Previous, I think someone has doubt. It should be P implies Q is true, then it's true. I don't know. Mayank is asking me. So for previous, it should be P implies Q is true. Mayank, can you further ask me what you've been asking? P implies Q and Q, then Q. If P implies Q and it is known that P is true, we infer that Q is true. And if P implies Q and it is known that Q is false, then we conclude that P is false. This is conclusion. If you have any doubt, you can write further. Mayank, you can write further if you are not convinced with this. We'll go back to that. Okay, fine, good, fine. Moving to the next point, the Boolean algebra, De Morgan's laws, etc., can be used to derive calculus of such proposition. And the connectives which are there in propositional logic, they are not, and, or, implication, bidirectional implication. Here we have defined this implication. A very standard definition of implication operator is there. This is one of the operators in propositional logic. The operators or the connectives that are there in propositional logic are and, or, not, implication, and logical equivalence or bidirectional implication, both way implication. And the definition just only says, you know this very well. X, Y, X implies Y. X implies Y is logically equivalent to not X or Y. And only for the second row, when X is true and Y is false, in that case only X implies Y is false. For remaining three entries, it is true. This is a truth table of implication, very standard thing. Next, we show the connectives which are there. Yeah, the operators or the connectives which are used in propositional logic, as said earlier, they are not, the symbol is mentioned there, and, or, implication or implies, and the operator that I have not mentioned, which is not visible actually, that is if and only if, or double arrow, putting this less than before this implication. So it is bidirectional arrow, also called logical equivalence, also called bidirectional implication, also known as if and only if. In many statements, particularly in a theorem, you must have noticed if and only if. It means A implies B and B implies A. That is logical equivalence. That is bidirectional implication. That is if and in only if. These are the connectives or operators that are used in propositional calculus. Moving further, now we'll represent some very simple English sentences in propositional logic. Already you know. Yeah. statement that will represent this English sentence will represent as an expression in propositional logic. Already you have done this in TOEFL in the last semester itself. You have done this. Just for the refreshing purpose, we are writing it again. If either Jerry takes calculus or Ken takes sociology, then Larry will take English. Do not reply in this chat box. Just take few minutes. Let others also realize this. Do not write the answer in the chat box. The statement, the sentence that is given to us is, I'll ask you to write it. You can write at that time, not now. Let others think for a while. The sentence that is given to us is, if either Jerry takes calculus or Ken takes sociology, then Larry will take English. We need to represent this sentence as an expression in propositional logic. We know the propositions, we know the connectives or operators that are there in propositional logic, those 5 connectives. Not, or, and, implies, double implies. These are the only operators. These are the only operators that you can use in propositional logic. So it's it is a very simple. We can split this sentence into the parts. Jerry takes calculus can be represented by any proposition. Any name can be given. Here, for simplicity, I have used the proposition P. I could have used any proposition like Jerry. Anything can be written. Fine. So the fact Jerry takes calculus is represented as P. Ken takes sociology is represented as Q, and Larry will take English may be represented as R. Now anyone can write. Very simple to write this. Either Jerry takes calculus or Ken takes sociology. Jerry takes calculus is P. Ken takes sociology, that is Q, and it is either or. So logical or. P or Q. Conclusion is, yeah, definitely correct. P or Q implies R. Correct. Fine. You got that. Very good. P or Q implies I. Only maybe these connectives, the symbols that are used, more popular symbols that are used, I have used for or. Plus is also there, but this is more popular used. Fine. P or Q implies R. Next, crop will be destroyed. Crop will be destroyed if there is flood. May not be visible. The top portion doesn't matter. The sentence is, the crop will be the crop will be destroyed if there is flood. The crop will be destroyed if there is flood. So again, there is flood, and the second part, the crop will be destroyed, can be represented as proposition P and Q, and this becomes simple. P implies Q. Conclusion condition is if there is flood. So after if, always there is a condition. So there is flood, that is represented by proposition P, and the conclusion is the crop will be destroyed. The crop will be destroyed, represented as proposition Q. So it is P implies Q, or if P then Q. That is the meaning. So these are simple representation of sentences in propositional logic. You must have done even complicated sentences in the first chapter in theory of automata formal language subject. Next, we try to understand which is more, what exactly is nearer to the expression P implies Q. Here are some of the possibilities. Among the given, which is the meaning for P implies Q? Is it Q is necessary for P? Is it P is sufficient for Q? Is it P only if Q? Is it Q if P? So I think 2 of them are visible to you. 2 options are visible to you. Don't write in the chat box. My expression is P implies Q. What does it mean? What does that mean? Is it Q is necessary for P? Option number A, that is visible. Option number B is P is sufficient for Q. The third option, which is partly visible, it is P only if Q. The fourth option, which is not visible to you, it is Q if P. Among these, which is more closer to P implies Q? You have to think about this for a while. P implies Q means Q is necessary for P, is sufficient for Q, P only if Q, Q if P. These are four options. These are four options. Now I think someone, anyway, you have been writing this. The answer which I have got from Jaimeen, from Devang, it is B. P is sufficient for Q. Let us see whether it is B and D, many B's, some D's. So options are B and D. The correct answer seems to be B and D. Let's see what is B. P is sufficient for Q. If P, then Q. So given P to be true, we can conclude that Q is true. So P is sufficient for Q. That is the meaning for sufficiency. If P is found to be true, then Q becomes true. That is meaning of P is sufficient for Q. And that is correct. Definitely that is correct. Option number D, it is Q if P. So I think if P then Q, instead of that, we are writing conclusion first, Q. If P, we are discussing option number D, that is not visible to you, and that option is Q if P. So here P implies Q is if P, then Q. So here we are writing if afterwards, but then it is if is associated with P. If P, then Q. So D is correct. Definitely D is correct. D is definitely correct. D is also correct. D is also correct. Let us see what is Q is necessary for P. Or let us discuss option number A. Q is necessary for P. Go back to our modus tollens. P implies Q. Given that not Q, the inference or the conclusion is not P. So if Q becomes false, then the conclusion is P is false. For P to be true, Q has to be true. And in fact, A option, Q is necessary for P. That is correct in the context of the definition of modus tollens. Q becomes necessary because if Q becomes false, going back to the modus tollens law, if Q becomes false, our conclusion is P is false. So for making P to be true, I have to make Q to be true. Q is necessary for P. Option number A is also correct. A, B, D correct. And option number C, P only if Q. I'm going to the, actually all the answers are correct. All four are equally meaning P implies Q. All the four answers are correct. That was scrolled down earlier by mistake. Yeah, all the answers are correct. And here I'm just giving some examples. Only if, use of only if. If you are, yeah, the statement which is there is, if you are beheaded, then you will die. If you are beheaded, then you will die. It is same as you have been beheaded only if you die. If you are beheaded, then you will die. You have been beheaded only if you die. Only if it is same as implies. You have been beheaded only if you die. That is example for equivalence between P implies Q or if P and then Q, and P only if Q. Again, Q has to be true only if Q. Q has to be true for P to be true. P only if Q. Again, the same concept of modus tollens. P only if Q. Now, moving further, we take some examples of PL sentences. It is given that it is hot. It is also known that it is humid. It is given that it is raining. It is hot. It is humid. It is raining. So we are representing these sentences as prepositions. So our prepositions could be hot. For it is humid, it could be humid. We can represent it is raining by raining. Our prepositions that we have used are hot, humid, raining. We could have used any name as per our convenience and choice. The sentence it is hot, we are representing using hot. It is humid, we are representing using humid. The sentence it is raining, represented using raining. I could have used only R, my choice. The next information that is given to us is if it is hot and humid, then it is raining. Again, we are writing this sentence as a representation in propositional logic. Whenever, please note that whenever it is if then, we must put implication. And here also if then is there. If it is hot and humid, then it is raining. The preconditions are hot, then we have and humid. So it is and, these words hot and humid, they are connected with and relation. So my representation becomes in parenthesis hot and humid. And then the next part of the sentence is then it is raining. So then it means conclusion. So implies raining. My representation for the given sentence, if it is hot and humid, then it is raining. It is hot and humid implies raining. Please note that and implication are connectives or operator of propositional logic. There are 5 operators of propositional logic and an implication. These two are part of that. We can only use these 5 connectives only while representing any sentence in propositional logic. We can use these connectives or operators only. Next sentence is if it is humid, then it is hot. Again, if then, very simple. Humid implies hot. The next sentence. Next, we move to the